stunning video shows how much Earth has changed in 1.8 billion years by Alan Collins on The Conversation. Using information from inside the rocks of Earth's surface, we have reconstructed the plate tectonics of the planet over the last 1.8 billion years. It's the first time Earth's geological record has been used like this, looking so far back in time. This has enabled us to make the attempt at mapping the planet over the last 40% of its history, which you can see in the animation in the article. A beautiful dance, mapping our planet through its long history, creates a beautiful continental dance, mesmerizing in itself and a work of natural art. It starts with a map of the world familiar to everyone. Then India rapidly moves south. It's Pangaea. It starts off with Pangaea, then India rapidly moves south, followed by parts of Southeast Asia as the past continent of Gondwana forms in the southern hemisphere. Around 200 million years ago, Ma or Mega Annum in the reconstruction, when the dinosaurs walked the earth, Gondwana linked with North America, Europe, and Northern Asia to form a large supercontinent called Pangaea. And then the reconstruction carries on back through time. Pangaea and Gondwana were themselves formed from older plate collisions. As time rolls back, an earlier supercontinent called Rodinia appears. It does not stop here. Rodinia, in turn, is formed by the breakup of an even older supercontinent called Nuna about 1.35 billion years ago. Why map Earth's past? Among the planets in the solar system, Earth is unique for having the plate tectonics. Its rocky surface is split into fragments and plates that grind into each other and create mountains or split away and form chasms that are then filled with oceans. Apart from causing earthquakes and volcanoes, plate tectonics also pushes up rocks from the deep earth into the heights of mountain ranges. And this way, elements which were far underground can erode from the rocks and end up washing into rivers and oceans. From there, living things can make use of these elements. Among these essential elements is phosphorus, which forms the framework of DNA molecules, and molybdenum, which is used by organisms to strip nitrogen out of the atmosphere and make proteins and amino acids, building blocks of life. Plate tectonics also exposes rocks that react with carbon dioxide in the atmosphere. Rocks locking up the carbon dioxide is the main control on Earth's climate over long-term scales, much longer than the tumultuous climate change we're responsible for today. A tool for understanding deep time, mapping the past plate tectonics of the planet is the first stage in being able to build a complete digital model of Earth through its history. Such a model will allow us to test hypotheses about Earth's past. For example, why Earth's climate has gone through extreme snowball Earth fluctuations, or why oxygen built up in the atmosphere when it did. Indeed, it will allow us to much better understand the feedback between the deep planet and the surface systems of Earth that support life as we know it. And we have so much more to learn. Modeling our planet's past is essential if we are to understand how nutrients became available to power evolution. The first evidence for complex cells with nuclei, like all animal plant cells, dates to 1.65 billion years ago. This is near the start of this reconstruction and close to the time the supercontinent Nuna formed. We aim to test whether the mountains that grew at the time of Nuna formation may have provided the elements to power complex cell division. Much of Earth's life, photosynthesis, and liberates oxygen. This links plate tectonics with the chemistry of the atmosphere, and some of that oxygen dissolves into the oceans. In turn, a number of critical metals like copper and cobalt are more soluble in oxygen-rich water. In certain conditions, these metals are then precipitated out of the solution. In short, they form ore deposits. Many metals form in the roots of volcanoes and occur along plate margins. By reconstructing where ancient plate boundaries lay through time, we can better understand the tectonic geography of the world and assist mineral explorers in finding ancient metal-rich rocks now buried under much younger mountains. In this time of exploration of other worlds in the solar system and beyond, it's worth remembering there's so much about our planet we are only just beginning to get a glimpse of. There are 4.6 billion years of it to investigate, and the rocks we walk over contain the evidence for how Earth has changed over this time. This first attempt at mapping at least 1.8 billion years of Earth's history is a leap forward in the scientific grand challenge to map our world, but it's just that, a first attempt. The next years will see considerable improvement from the starting point we have now made. The author would like to acknowledge research was study done by Xanthi Kao, Sergei Pisarevsky, Nicholas Flamant, Derek Hasterrock, Dietmar Müller, and Sanzon Lee as co-author. He's just one cog in the research network. Also, the author acknowledges many students and researchers from the Tectonics and Earth Science group at University of Adelaide in Australia, and national and international colleagues who did the fundamental geologic work this research is based on. This is by Alan Collins, Professor of Geology, University of Adelaide, on the conversation on Science Alert. Please leave your comments, and thank you for your support. Finally, support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.